Yeah, we started now, Neil.
Okay, thanks very much. So good morning to everyone out there. Great that you're able to join us for this online webinar supported by SuperGen Super Solar. And I'm just going to, first of all, before we start with the programme, just take you through a few initial slides just to update you on a few other activities before the actual speaking starts from our invited speakers. So this is the online webinar for New Horizons in PV using organic materials number 3. So we started these a couple of years ago during the pandemic, and they proved popular. So we've continued. We've continued in this online mode because it really makes it very accessible for everyone to join very simply. So our speakers today will be Professor Emilio Palomares, Professor Ji-Sun Kim, and Professor Moritz Riede. Unfortunately, Rachel Evans has had to pull out, so we're only going to have 3 speakers today. Each speaker will have approximately half an hour slot, so if you want to think about timings, that's more or less how we're going to run things, although we could be a wee bit more relaxed because Rachel's not able to join us. We have a bit more time than we expected. So that's our activity today. Wait till I move on the slides. Before going into that programme, let's run through a few other activities that are coming up shortly, just to publicise a few other opportunities to you all. So SuperGen Super Solar in general is the UK network for those interested in solar energy, free to join, open to all, currently around 750 members, so really a huge UK based community supporting all things solar. Newsletters with updates and events, funding opportunities, international conference support, and some free places at some events. So let's have a look at some of the details for that. All of this is captured on this website here, so if you're really interested in anything on the slides that follow, you'll find further follow-up information on the website. So there's an international conference fund up to £500 towards the cost of attending an international conference if you have a oral or poster presentation to give. And that's for those registered and employed at UK universities and members of the Super Solar Network. But of course, as I've just said, joining the Super Solar Network is free. So if you're at a UK university, you can join up and apply for this fund. Only a few places left. The events must take place before the 30th of June this year. So if you're interested in that, dive in quickly. There is a childcare fund as well to assist those with childcare responsibilities with the costs of attending conferences. So where there are additional costs, for example, because of participating on what's normally a non-working day or extended working hours, etc., overnight stays, these things can be supported with up to £500. There are a couple of events coming up. This one in particular, Research Methods for Solar PV 2023. Again, this is part of a series of events and really focuses on practicalities of solar PV. And you can see a number of different topics here from expert speakers in machine learning, spectroscopy optics, IV measurements, bifacial PV modeling. So a series of expert speakers giving real insider knowledge of the detailed expertise required in these particular areas. So very practical. So on Wednesday, the 19th of April. I expect most of you will know about PVSat 17, so that's linked with Super Solar. So the Super Solar PVSat conferences are running together, and there are a limited number of sponsored free student places available. So some of my students have already taken advantage of this. There's still some of these places left available. So again, dive in quickly if you are a student or you're supervising students who would like to attend this conference for free. Still a few places left. And I expect there'll be a lot of awareness around the fact that HOPV this year is in London, so a UK-based HOPV, so great opportunity for the UK community in particular to get involved in what is one of the flagship conferences in the perovskite and organic field. So Poster abstract deadline 15th of May. I think the speaker deadline is today, perhaps very soon, but perhaps it might be today. So if you still want to put an oral abstract in, you'll need to get moving quickly. But poster abstracts up until 15th of May. And PSCO, so all things perovskite related to solar cells, but beyond that also into wider optoelectronics, again in the UK, in Oxford in September. So there's a website here, so you can sign up to that as well if that's your thing and you're interested in that conference. So back to today. So we have our third in the series of New Horizons in PV using organic materials. Our focus is not just OPV, which is the obvious thing using organic materials, but the other types of technologies where organic materials comprise one of the layers or one of the modifications to make other PV technologies also work or work better. So we have a series of broad talks across those themes. We can see some titles here, very well-known high-level speakers who are going to deliver these. Although, as I said earlier, unfortunately, Rachel's not able to join us today, so we'll just have the three talks as listed there. So that's me taking enough of everybody else's time. I've managed to successfully stop sharing my screen, so I'm going to pass it over to Emilio, who will be our first speaker.
Okay, so everybody can see my screen?
Yes,
okay,
it's fine.
Excellent. Yep, the first thing I did was to annoy Neil. I changed the title of my talk. So I'm sorry, Neil, but it will be about some molecules as a context for perovskite solar cells. So, well, let's start by the acknowledgement, because usually I talk too much and I never have time to really acknowledge the people who does almost all the work in the research group, which is these people here in the picture, and also the companies that are supporting us now with the research of the decarbonization of chemical processes. I mean, converting CO2 in valuable chemicals using sunlight. So perovskites, as Neil said, most people that work on this field, they came either from the solar cells or organic solar cells. I still remember the times in this office when Moritz and I, we were discussing about the use of small molecule organic solar cells in the solution process were evaporated. But then it came the tsunami of the perovskites, and of course, efficiency matters, and those materials are able to convert sunlight into electricity in about 23% efficiency, and that's why they attract a lot of interest. And in fact, it's an example of the only semiconductor which is known that has an X-ray structure as a solid and has a Raman as a liquid, as a toluene. And for me, this is an amazing property of these materials, and still we have not yet fully explored all those properties of these hybrid perovskite materials. This is a very old slide where basically you have the 4 types of devices that you can make using these perovskite materials. Basically, I believe that nobody uses anymore the mesoporous titanium perovskite, and then people has focused on what they call thin film perovskite solar cells. And basically, our goal has been to replace as many as possible layers based on organic semiconductors, because they usually are the ones that degrade under light and oxygen. So this N-type or P-type contacts, we try to replace it by a small molecule, which are more robust and also can act as a good contact to keep the same efficiency in perovskite solar cells. And this is kind of the example, the paradigmatic example we published in 2019, when we replaced the whole transport material that usually was PDO-PSS or was spirontat, but these 2 molecules, very simple to make. You can scale up this in kilograms, even in the lab, and the chemistry is easy. And of course, you have to work in what is called inverted perovskite solar cell structures. Basically, it's inverted because you collect the holes in the ITO and the electrons at the metal contact. And this has become very popular. And basically, there is now a lot of examples of other molecules that also achieve high efficiencies. mainly I will divide, I put examples here of molecules that are commercially available. So this molecule was sensitized in our lab, but we never thought about this as a commercial product that we didn't patent, but the Chinese people did. And you can find it in actually Lumtech. And also those molecules here, which they use phosphonate groups rather than carboxylic groups, which are also commercially available. Those three molecules, I would say, are the most common use self-assembled molecules for perovskite solar cells. The process to make these contacts is rather simple. So you really can do it in the lab or even in larger scale using a slowed coating. So you get the ITO or your transparent conducting oxide, you dip in a solution containing the molecules, you rinse with the same solvent, you dry with nitrogen, and then you do all the steps towards the fabrication of the solar cells. In fact, the people in Germany, they also use this process to make the silicon and perovskite tandem solar cells using the small self-assembled molecules as a contacts, and they achieve the record efficiencies of these tandems. So the last example of that we have been working was to substitute the spiroOMTAT by a molecule that actually has the same structure as the spiroOMTAT, and that was in a collaboration with a group in Glasgow, the Professor Graeme Cook. And basically, this is the efficiency of the perovskite at that time. So it was about 25.2% using this spiroOMTAT, and PTA, which is a polymer, about 22%. With the spiroOMTAT, the reproducibility of the devices is very high. With the PTA, it's not that high, but it's true that in both cases, you have issues with the stability. So basically, also there are also concerns when you go to industrial scale, which is the high cost of the PTA, and also you have to bear in mind that the PTA is quite hydrophobic, and then it's not easy to put on top of the perovskite. With the spiroOMTAT, the cost is not as expensive as the PTA, but it still is quite prohibitive to be commercially available. And the efficiencies were lacking about 16% in most of the cases. That's what you get in large areas. So the idea was, well, here is the processes that, for example, people like Said Hack has studied quite a lot at Imperial College about the degradation of the perovskite solar cells, and they come out with this hypothesis that you oxidize the spiroOMTAT with the salts, and then you also need to have dopants. You really want to have high efficiencies, but the presence of dopants also makes the cells to be unstable. So it's kind of a compromise. You want devices with long lived. You don't need to use dopants, but then your device efficiency is rather poor. So discussing this with Graeme Cook and Michel Cariello about how we could replace spiroOMTAT, they come up with the idea to sensitize the spiroacid, which is really starting from the spiroOMTAT in a simple steps. You actually can end up having a carboxylic acid. This is a straightforward reaction. You can buy 1 gram of spiroOMTAT, and you do the reaction, you can have enough material for the next 10 years if you work with the spiroacid as a self-assembled monolayer. This is the structure of the device. So you really have to replace the PTA or the spiroOMTAT by the SAM. The spiroacid has a little bit shift the oxidation potential, and that has an effect on the VOC of the cell, as you will see later. But the nice thing is that it becomes much more stable than the films of the spiroOMTAT. Here is some examples of efficiencies of these spiroacids, the SAMs of the spiroOMTAT. So you can reach efficiencies high. This is an average of more than 1,000 devices, and you can reach efficiencies about 19% with the PTA, with the spiroDOPT, with the spiroDOP, and the spiroacid. You get efficiencies about 70%. So it's not that far from what you get from the PTA, but the cost is much cheaper. The current basically is the same. The fill factor actually is much better in the spiroacid. This is one of the best fill factors you can actually achieve using perovskite solar cells. The issue is the voltage, because, as I said, the spiroacid has a little bit different voltage than the spiroOMTAT. But it's important to notice that either spiro doped or undoped, they have much lower VOC, and the efficiency actually is rather poor in inverted perovskite solar cells. Of course, if you use the normal regular structure, you can make this 23% that people has claimed a few months ago. So here is the IV curve. Nice thing about the working with the SAMs is that you avoid this process called hysteresis, which is rather important when you work on modules. You have hysteresis or large hysteresis in modules. This is really an issue. When you work with the self-assembled monolayers, the hysteresis is almost negligible. And the efficiency, and this is real efficiency, is quite good. I mean, like for 600 hours at bias, you have devices which is seal devices, but not on the nitrogen, just measuring in the seal devices. It's rather, I believe, remarkable. One thing that we observe is that, as I was saying, to deposit these organic materials on top of the perovskite, you have different angles. And as you can see, the highest angle is the PTA, and that makes very challenging to make good efficiencies when using PTA on perovskite, which I believe will be an issue when you want to go to modules. This is on photophysics. I'm sure people from James Darran group will love that. We still have arguments about why this quenching of the luminescence of the perovskite when you have the SAMs and is due to, so some people believes, and I agree with them, that having the SAMs in the ITO before making the perovskite layer, it makes a difference on the way that the perovskite grows. So in a way, you are modifying the crystal structure of the first seeds of perovskites, and that makes that the first few nanometers has a huge impact on the transport and also on the way that the charges are collected. But you know, we haven't come up with a technique to study such things, which is not luminescence. So the only thing that we can say is that when you have the SAMs, actually you have a very nice quenching or charge extraction of the charges at the interface with the perovskite and the ITO. So here also some data about the charge extraction and recombination, the famous TPV, and you can see for the TPA and the spiro acid are almost alike. The same happens with the charge. For the spiro doped and the spiro acid, the recombination is faster. Also, you have changes on the charge extraction and the charge distribution on the different voltages. So here is what it matters to us most. This is the time, 100 hours, when we analyze the efficiency, long-term stability without night and day cycles, just on the solar simulator once and 100 hours. And you see that the spiro acid has some nice features that increase the efficiency and then is very, very stable. The same happens with the TPA, although the TPA starts some degradation, and the performance of the spiro acid, even undoped, is rather poor in inverted solar cells. And you also can see this by eye, because the films with the spiro OMTAT, they become yellow, so they are fully oxidized, and then most of the perovskite is converted rapidly in lead iodide. Why was the challenge for us using this perovskite solar cells? So what was our goal? Our goal was not to compete with people on efficiency. Our goal was to use those solar cells to power catalysts that can either make water oxidation, or, as the last example I will show today, do CO2 reduction. So basically, we combine two of these solar cells, and for example, a quarter of the sun, so 0.25 suns, we got efficiencies about 17–18%, and we have enough current and voltage actually to drive this water oxidation with a ruthenium catalyst. This is the IV curve of the tandem cell. This is the electrocatalysis. This is the point where actually you have to work in order to have the catalytic process going on. And this is a classical or rudimentary system we work to do the water electrolysis at the ICIQ. This potential stat is what you change by a solar cell. Basically, this is the on and off we observe when we do this And at that time, what we see was this kind of spike and then recovery. And then we learned from a paper published by Michael Gratzel that was due to the ion migration on the perovskite solar cell. So in order to avoid that, you have to use chopped light. When you use chopped light, then you don't have this issue, and you still can have this solar cell as a, let's say, power source for the catalysis. This is after and before the formation of hydrogen from water. This is the IV curves after, before, and after the use as a power source for the catalysis. And this is how the current change over 200 seconds, which is what we use to do the catalysis. So here is what I was telling you about the chopper light. So here is a zoom on this area. We ran the experiment for more than 10 hours. So here is only about 5 hours, and it's really, really stable. So we got at that time a solar to hydrogen efficiency about 13.6%. At that time was the record. And then after we published the paper, the people from Thomas Jaramillo in Stanford, they use a gallium arsenide solar cell with a similar ruthenium catalyst, and they overpassed this number by, I think it was 15% is the record right now. So this is the Faraday efficiency in oxygen, what should be in theory, and what we get. And this is in theory what the hydrogen we should get, and this is in fact. So we know that it's not a perfect system, we have some leaks, but I think it's a good way to actually combine solar-driven water splitting systems with wires, of course. I mean, like doing everything in one single material is much more challenging. From that, we move towards combination of organic solar cells, which I will not talk today because the lack of time, and perovskite solar cells. The idea was to combine the best of the two worlds, the organic solar cells and the perovskite, and then have enough power to do a more challenging reaction, which is like the reduction of CO2. So here is the materials that most people working on organic solar cells, they know. So the non-fluorine acceptor, which people now has reached about a 16 or 18% efficiencies. We did some work with a colleague of us in the Basque Country, in the Polymath, to change and mix those non-fluorine acceptors with these fluorine acceptors in order to increase a little bit the current of the devices, because for tandem solar cells, you want the current to be high. And that's what we get. We get devices which were about 16% efficiency, 17% efficiency. The idea behind that, obviously, is to combine the perovskite and organic solar cell. So we have a panchromatic device with high current and high voltage. And well, we connected, and this is results we achieved last week in a master student, Joan Marc, which is now doing the PhD, and a postdoctoral fellow that now has got a position as a professor in Trieste. And here you can see from CO2 and using tandem solar cell based on organics and perovskite as a power source, we got quite nice yield for ethylene, for methane, some CO and some hydrogen. And the challenge is, of course, to reduce the hydrogen you form, which is difficult because the more current you need, the more hydrogen you produce. And what is missing here, actually, to arrive to the 100% Faraday efficiency, is because this was measuring the gas phase, and we're still analyzing the liquids because we want to know how is the catalytic cycle. So we have detected some formic acid, and also we like to know this formic acid where it's coming from. And with that, I think I'm on time. So I thank Neil and all the organizers for the invitation, and I promise that as soon as I can, I will do my visit to Edinburgh with my wife, as I promised many, many years ago, Neil.
Thanks very much, Emilio, and I'm looking forward to that visit to Edinburgh. So thanks very much for keeping to time. That's great. There's questions appearing in the questions and answers. So I don't know if anybody, maybe I'll just read them out in case there's anybody who can't see that. So from Ravi Misra, query about the current density of your tandem device and how high the current OPV helps in current matching.
Yeah, I mean, like for what we have calculate and estimate together with the people who works on catalysis, for CO2 reduction, you need about 15 milliamps, and then the voltage you get is about I mean, the best you can get, it's about 2 volts, 2.2 volts. The issue is that, of course, you need to have a very good catalyst that works at 2.1 volt with the 50 milliamps. So that's what we try to get. Okay, it's challenging. So we don't get always in all the devices these high currents. 50 milliamps is a high current for a tandem with organics and perovskite. And sometimes when we get higher current and less voltage, we have to combine the two tandems to get the voltage. But then the problem is that you have much current and you have a lot of hydrogen. So it's still not optimized. I mean, for the water splitting is rather easy. I mean, water splitting with the 2 perovskite, you have enough material. So you get about 1.9, 2 volts. And with the ruthenium catalyst we use from Tony Llobet, you can run the catalysis in 1.3 volts. And the current, I mean, we were using quarter of the sun, so you almost don't need current to drive this reaction. The issue with the CO2 reduction is the voltage, actually. So you need too much voltage really to do the reaction. You need over 2 volts. So it's complicated. But I will not be able to say right now what will be the optimum for CO2 because it depends very much on the catalyst, really.
Okay, thanks. I've got a question. Just about the hysteresis. You get the low hysteresis when you use the SAMs, and is there any understanding of why that is?
The SAMs is still a mystery. I mean, Antonio Abate and I, we have been working on SAMs in the last, I would say, 4 years, and we still have a lot of debates when we have these regular meetings about what the SAMs does. Nobody knows. So the thing is that Antonio believes that the SAMs, because he was on team-based perovskites, okay? And then for team-based perovskites, for example, recently has been a paper published with a tripodal molecule that makes the team perovskite in a 2-step process very efficient. But they don't explain why. And Antonio believes that the reason why it works good in perovskite solar cells, including the tin oxide, is because you modify the crystal growth of the perovskite layer, the first nanometers, if you have the SAM. Somehow this is key for all the rest of the processes. So it's like you have kind of a hybridization molecular orbital between the SAMs and the crystals you grow on top. But we don't have much information because we try to get to synchrotron and we see nothing. And of course, when we do photophysical measurements, they have many interpretations. You know, you can say that the luminescence is quenched because the crystal changes or because the charge transfer is better. So it's the question, no? But I think in the future it will be solved because we are working on different SAMs where chemistry is involved in order to address this question. How is the interface between the SAMs and the perovskite?
Okay, thanks. And there's another question in the chat, in questions and answers, about the anchoring mechanism for the SAM on ITO.
How is the mechanism of the SAM in the ITO? So how is anchored?
Anchoring mechanism, yeah.
Yeah, I mean, it forms spontaneously a covalent bond. So when it's formed, it's really difficult to detach. In fact, it's so difficult that we scratched we had an idea that was to send samples to 1,000 megahertz, 1 gigahertz NMR to study the interaction of the perovskite with the SAMs, because by NMR this can be seen, and it's so well attached to the ITO that even if you scratch, you don't get any SAM signal on the 1 gigahertz. So it's spontaneous. It's kind of the same as happened with the Gratzel solar cells with the titanium dioxide. So you form a covalent bond and it stays there. I mean, like, it's not an issue. Now we work in a variation of the SAMs, which is based on click chemistry. And the click chemistry, you know, using copper catalyst. And the idea is to modify those SAMs in order to interrogate with the SAMs how is the interface, you know, like being able to change the crystal structure a little bit. And for that, you know, you would use click chemistry with the azide and the triple bond and the copper.
Okay, there's no more questions in the chat and Q&A, so it's online, so you don't get a big round of applause, you just get a clap from me. So well done, Emilio, and Jason as well. Okay, thanks very much.
The nice thing is I can get a coffee in my office while I look at the lecture of Jason.
These online things are great. I love them. Okay, thanks, Emilio. So our next speaker is Jason Kim from Imperial College, and Jason will share her screen. And in your own time, Jason, off you go.
Okay, let me just try to get my okay, laser pointer. Okay, thank you very much.
Can you, you're on presenter mode, can you
Oh.
project it?
Okay, let me on now.
Well, actually, it's that's it. That's perfect. Thanks.
Is it okay? Okay. Right. Let me see whether I can laser pointer. Okay. Okay, thank you very much, Neil, for inviting me to this PV technology kind of a workshop. So today I'm going to talk about this key molecular structure perspectives for particularly the organic semiconductor-based photovoltaic materials. I'm trying to.
So just to say, slightly quiet. If you could maybe speak up a wee bit, that would be good.
All right. I'm not very sure why my computer. Is it okay now?
It's okay now. That's fine. Thanks.
All right. Okay. So as Emilio already mentioned, of course, very interesting kind of photovoltaic materials, and organic semiconductor is one of them. Organic semiconductors can be used as a photo conversion device material, not only for solar cells, but also for photodetector and solar fuel devices. So today I'm going to talk about two main key interesting issues related to organic semiconductor-based photovoltaic materials. First of all, non-fluorinoceptor, particularly focusing on their photostability, strongly dependent on molecular structure. And then the second part, I will touch why this particular NFA, such as Y6, is so special in terms of photo conversion efficiencies, like photovoltaic properties. So there has been a lot of progress using organic semiconductor as a photovoltaic material, achieving already more than 90% of the power conversion efficiency. And then this significant progress is based on development of these new non-fluorinoceptors. There are mainly three different non-fluorinoceptors, as I've shown here: IDTBR, ITIC, and Y6 families. As you can see, they have a very strong donor acceptor character along the main backbone, more linear structure of IDTBR, and linear but with bulky side groups in ITIC family. And then 2D-like shape, banana shape of Y6 family. Even though in terms of efficiency, we can achieve high enough values, but still there are a lot of unknown and lack of understanding in terms of stability. So today I'm going to talk about in the first part, how these different very minor molecular structure affect the photostability, therefore the device performance. So molecular structure dependent to photostability. I will take a look at and discuss with you three important molecular structure differences. First of all, molecular planarity. So when you look at the IDTBR and IDFBR, just by changing the one particular unit in the molecular structure, like from thiophene to benzene ring, you can change its conformation or molecular structure from the planar to the twisted structure. Does this planarity matter for photostability? Also, even though you initially have a very planar structure, but certain molecules can still change its structure because it's less rigid. So I will compare two planar molecules with a different degree of rigidity and their impact in photostability. And finally, you can actually change a lot of optoelectronic properties by putting less or more electron withdrawing end groups. So what's the impact of this end group on photostability? So in order to look at this molecular structure dependent photostability, we consider very fascinating molecular nature of organic semiconductor, meaning that when you actually excite either charge injection or photoexcitation, the molecule changes structure in order to adopt this excited state. So we use this molecular structure lattice changes associated with photoexcitation in order to look at their stability. So first, let me compare the planar molecule with the twisted molecule. What we found is there is this initial photo-induced conformational change of the molecule before there is an irreversible optical or structural change happening in the molecules. And then another thing is, if you compare planar molecule with a twisted molecule, this initial molecular structure or conformational change is much faster in twisted molecule. So this comparison with the planar and twisted molecule, we understood that such a structural change comes from the unit where there is no side chain attached, so very easy to rotate, for example, in the benzodiazole unit in IDTBR NFA materials. This conformational change, particularly the BT unit twisting, will induce the conformation from the planar, more twisted structure. When you twist the molecule, of course, there is a more high probability for oxygen and water atoms to diffuse and then cause this irreversible degradation. This conformational or molecular structure change upon excitation is really important because it will change your electronic energy level as well as optical properties. So even though you start with a very planar molecule, while you are exciting the molecule, it changes its conformation. Therefore, your HOMO and LUMO energy level also changes. At the same time, reducing your absorption, particularly low energy CT state like transitions. Second, when we look at the planar molecule, but with different degree of rigidity. So here I compare planar ITBR with the planar Y6 molecule. As you can see, when we do some simple calculation, the IDTBR is able to adopt different conformation when you twist the molecule. Compared to that, in Y6 case, there is this one global potential minima, suggesting the Y6 molecule is conformationally very rigid. You cannot actually twist easily. This conformational rigidity and uniformity will induce this conformational order, therefore reducing the energetic disorder. It can be seen in the in experimental data when you measure the subgap trap state, Y6 showing the lowest subgap trap state, indicating this rigid structure induced energetic disorder decrease. And when you make this planar and rigid molecular structure, surprisingly, the molecules are really stable under photoexcitation. So making planar and rigid molecule is really good for photo conversion devices. No, we have to be quite careful. When we make a rigid and planar structure, of course, molecule has a tendency to have a very strong intermolecular interaction. And also, if you use a planar molecule without kind of bulky side group in the blend with, for example, like a C60, it can also form kind of adduct structure. Those either intermolecularly kind of axiomatic state formed or adduct state can induce lower energy subgap state. So when you operate your device on the low level, these trap states can be very problematic. So On the highlight, the planar molecule give a much faster transient or photocurrent. But when you lower your light intensity, then it actually produces much slower transient. So your image sensor, for example, your mobile phone, when you operate under very low light, it will produce a very slow turn on and off characteristics, which is non-desirable for the device. So we have to be quite careful when we design the molecule. Finally, the end group effect. Here I show as an example of ITIC changing the end group structure from putting more and more like electron withdrawing end group atoms. What we found is that when you change the end group, you don't actually change the degradation mechanism. However, it slows down the degradation. So as you can see, the ITIC showing much slower state degradation compared to ITIC and ITIC dimethylized kind of molecules. Another interesting is the choice of these acceptors strongly affect donor polymer photostability in blend. The change we observed in ITIC is originated from, again, the rotation of a moving or movable kind of end group in ITIC. When it flips over, of course, it can form photo isomers in the molecule, which we also observe as a byproduct. The degradation pathway is energetically the same for all these three NFA materials. But as I mentioned, it shows different degradation rate. So what determines this degradation rate? When we put fluorinated, very strong electron withdrawing unit in the end, slowing down this degradation process. It turns out that there is a very interesting molecular electrostatic potential we have to consider. So because this ITIC molecule is a very symmetric structure, so in general, the NFAs have a very low dipole moment. However, when you're changing the donor and acceptor character by putting fluorine atom, for example, then you change the local charge distribution. Therefore, strong impact in the quadrupole moment, particularly pi-pi stacking direction. So when we calculate the quadrupole moment Q pi value, you can clearly see the strong dependence of end groups. And this strong Q pi value is very important because it determines very close intermolecular interaction between NFA molecules, also between NFA and donor polymer molecules in blend. In ITIC2F case, it changes donor polymer homoenergy induced or caused by this strong intermolecular interaction. Therefore, we considered that and proposed that this strong intermolecular interaction induced by NFA high molecular or high quadrupole moment enables this excellent photostability of NFA as well as blend systems. So in the first part, I briefly explained to you how important it is the molecular structure, particularly NFAs, in order to study the photostability. In order to enhance the photostability, we need to consider the design of a molecular structure, planar, rigid, and also different end groups. The second part, I will talk more about very specific NFAs, very well known and widely used Y6, giving very high the power conversion efficiency. As you can see, there is a very strong donor acceptor character along the main conjugated backbone of a Y6 molecule. There has been or still a lot of argument and discussions why this molecule is so special. In terms of free charge generation, barrierless charge transfer, and excited state like singlet and city state hybridization, non-dominated recombination, and so on. All these things were proposed as the kind of origin for high efficiency using Y6 NFAs. But I would like to consider two main things why this Y6 is so special. First of all, in terms of its energetics, as I mentioned before, these molecules, particularly with symmetric structure, we have negligible dipole moment. But because strong donor and acceptor character, we have still very high quadrupole moment, particularly pi-pi stacking direction. Differently from dipole, quadrupole case is a much shorter range electrostatic interaction you can cause because of 1/r cube dependence of potential. So if you don't have any kind of quadrupole effect, you can draw your energy levels as a straight line, HOMO and LUMO. However, if molecule has a positive quadrupole moment, it will pull down its energetics, energy levels. And if it has a negative quadrupole moment, it will push up its intrinsic energy levels. And because this is a very short range and strong intermolecular induced interaction, when you come from the bulk to the nearer the surface, this quadrupole effect will disappear, producing this quadrupole electrostatic potential induced band bending, which will influence your photophysics when you use this molecule. Another important thing to consider is the electronic state. Of course, you create the excitation through the photo excitation, so creating this charge transfer type of state. So how this charge transfer act in order to generate charge carriers or recombinations is another thing we need to consider. So for the Y6 case, when we first look at the energetics and calculating the Q pi value, we found that Y6 shows a really high quadrupole moment compared to, for example, alpha 60. It is because it has a non-uniform charge distribution because of donor acceptor character along the conjugated backbone. So having this high intrinsic positive quadrupole moment, as I explained, will influence the bulk energetics as well as interfacial surface energetics. Y6 is also very well known, having very strong intermolecular interaction. So when you consider solid state thin film, there will be a very strong interaction between end-to-end group or core-to-core groups of Y6 molecule, which will actually form intermolecular charge transfer, particularly emissive state. So we were trying to manipulate the energetics and then electronic state, particularly using different solvent. Using chloroform or chlorobenzene, we were able to control either more face-on or more edge-on kind of a structure. And when you measure energetics, you can clearly see almost 210 millieV HOMO shift of Y6 molecule. And then when you measure the ferroenergy level shift together with the HOMO energy level, that is one of the important characteristics of electrostatic potential effect, not dipole-induced vacuum level shift. And such energy level shift is also supported quite surprisingly very well with molecular dynamics. So when you put this differently oriented Y6 molecule using solution-based process and bilayer structure with the PM6, we observe it has a very strong impact on open circuit voltage as expected, because different quadrupole effect will push down with HOMO energy level with a different level. So the edge-on structure more pushing down. Therefore, the gap between the LUMO of Y6, HOMO of PM6 will reduce, reducing the open circuit voltage as we observed. However, compared to energetics we measure more than 200 millieV, we only observe around 110 millieV open circuit voltage changes. And it turns out that in the CF kind of a phase-oriented molecular structure, there is much less amount of charges stored, and these charges live much longer. And these things can be understood when we consider how this electrostatic potential disappears at the interface with the PM6 because of less electrostatic potential pooling of HOMO in CF case, you have less interfacial band bending. So even though you generate a lot of charge carrier, they will recombine much easily. So much less charges installed, and they live longer, shorter compared to Asian CB devices. So we can understand why this energetics and how this energetics influence photovoltaic device performance. One last thing, I mentioned that this Y6 molecule has a very strong intermolecular interaction. And you can clearly see when you change the concentration, the PL of Y6 shift. And this strong intermolecular interaction will formulate or form intermolecular charge transfer excited state. And this state, when Y6 core-to-core overlapping is strong in Asian structure, for example, this city state is strong bond. So we were thinking, are we able to use this energetic shift induced by quadrupole and then the strong intermolecular interaction forming this city state in order to make kind of a single component photovoltaic or photo conversion device in the same way as we have demonstrated using alpha-6 molecule. When you change its orientation, you have energetic even in the single component system, and we were able to demonstrate the use of this electrostatic potential for the organic photovoltaic devices. So we have done the similar thing using this solution processable Y6. So by quenching this emissive city state by applying the voltage, we can increase the external quantum efficiency of the device. Interesting is when you change NFA molecule with a different quadrupole magnitude, the quenching is reduced. At the same time, EQE gain is also reduced, indicating that our charge generation is originated from this city intermolecular state in Y6 molecule. And there was no strong, we observe linear photocurrent behavior as when you change the light intensity, indicating the absence of strong bimolecular recombination. So using those properties, we were able to demonstrate single component Y6 device working very efficiently as a single component organic photodetectors. Okay, this electrostatic potential will impact not only the energetics of NFA. When you make either bilayers or bulk heterojunction, it will also impact the donor counterpart in terms of its energetics, as I explained, because of band bendings. And we were showing experimentally the energy level shift of a homopolymer when you blend this homopolymer with a different NFAs with a different quadrupole moment. Okay, so today I discussed with you two different things: how important the molecular structure in terms of planarity, rigidity, and end groups to make much photostable materials. And second part, why Y6 is so special. And we considered the electrostatic potential induced and strong intermolecular interaction influencing this energetics and electronic energy levels. Okay, so I will finish my talk acknowledging my group members and collaborators and main funding sources. And finally, thank you for your attention.
Thanks very much, Ji-Sun, for an excellent talk.
Thank you.
let's have some questions. We've got a wee bit of time for questions. So we have one in the Q&A already from Pascal Kyenberg. Fantastic talk. Does the polymer also have a quadrupolar moment? How would having two species with non-zero quadrupolar moments change the energy levels and schematics at the interface?
Okay, so according to our calculation, actually polymers has negligible or much smaller quadruples. You can understand that because it has a much less kind of a inhomogeneous charge distribution in the conjugated polymer compared to NFAs, where you can actually manipulate each atom with a different charge density. And it looks like in the conjugated polymer, because of either elongated backbone or because of different atoms we use in order to control donor receptor character, in general, conjugate polymer shows much lower Q-pi values. And the second question was?
Well, the second part of that question was, I suppose, if the polymer did have a non-zero quadrupolar moment, would that be a good thing or a bad thing?
It depends on the combination of NFAs you use, because as I mentioned, depending on whether it's a positive or negative quadruple moment, either it can pull down or push up the energetics. So depending on what you would like to do, whether you want to increase the open circuit voltage or whether you want to reduce the energetic offset, so you will need to consider the polarity, whether it's a positive or negative Q-pi value. And also, you are not using conjugate polymer on its own. You all the time mix in bulk heterojunction or bilayer. So you need to consider relative impact of a quadruple moment with the NFA and then polymer. Yeah.
Okay, thanks. I just wanted to ask about, I suppose, relative importance of some of these different effects. And in terms of molecular design, I suppose the single most important thing I kind of picked up on was the importance of rigidity.
Mm-hmm.
And then that rigidity tends to also feed into strong intermolecular interaction because the packing can be good. Is that, would you agree with that? Would that be like the single most important takeaway message for those who want to design new molecules?
Yes. So rigidity-wise, we have compared planar and rigid. Of course, rigidity can be also obtained, even twisted molecule, if you fix the structure. So we are not saying you need to first make a planar structure with rigidity in the molecule. But if you make a planar and rigid, of course, you will obtain, you will gain in terms of intermolecular interaction. So if you are going to design the small molecule, with kind of planarity and rigidity, then you need to consider this high charge distribution, local inhomogeneity of charge distribution by putting more electron withdrawing and donating units, which will not cancel the quadruple moment. So rigidity is important, but you also need to consider this electrostatic potential influence induced by donor receptor character.
Okay, thanks very much. There aren't any more questions in the chat, and we're doing well for time, so let's finish there, and thank Jason again for an excellent talk.
Thank you.
And our third speaker is Maurice Rieder from Oxford University. Maurice.
Yep.
Oh, share your screen.
1 second. Sorry, can only take another 5 minutes. Glad that hope it doesn't crash. But here we go. Come on. I hope you can see my screen now.
Yeah, that's perfect. We can hear you clearly as well, so off you go.
Okay, well, Neil, thank you very much. And just like Emilio, I changed my title slightly, but let's get going. I'm going to present today about the electronic disorder in the organic solar cells we have been making. So brief outline of the presentation. Since we're one of the few groups working on vacuum deposited organic solar cells, I'm going to start with that, and then I'm going to work through the various disorders we observe. Just like with the previous speakers, most of the work and the heavy lifting has been done by someone else. In this work, in particular, Anna Jungblut, who's circled there, and of course, with our collaborators and funding. Now, vacuum deposited organic solar cells, we've heard a lot about solution processing. Before we make our solar cells in vacuum, we have the same powders, but of small molecules, not of polymers. We fill them into crucibles, and then we evaporate them in vacuum. We can control the thickness relatively well with thickness monitors, quartz crystal microbalancers. We can do co-evaporation, we can do triple evaporation, we can do gradients, and access to multi-layer stacks is relatively straightforward. So in terms of processing, yes, the equipment is a little bit more complex than a spin coater, but in terms of control, we've got quite a lot of control over what we do. Now, here are some of the stacks that are currently considered top performing in vacuum deposited solar cells, and you will probably notice two things. One of them is the efficiency is not at close to 20% as for solution processed solar cells, and of course perovskites are even higher. And the other point is the active layers are all relatively thin with 40 to 80 nanometers. So there are some bottlenecks which we're trying to solve and work on. One of them is why we vacuum deposited cells are struggling a little bit with fill factor when you go to higher film thicknesses. And of course, you would like to have a certain film thickness before for efficient light absorption, whereas solution processing does not have similar challenges. So we're doing a lot of work in the microstructural area on that. Another point is Jisong mentioned a material class which does not yet exist efficiently for vacuum deposited solar cells. So there are no NFAs, and NFAs have brought a lot of progress to the field and actually catapulted the efficiencies from 12% with fullerenes to around nearly 20%. So unfortunately, we don't have as yet. However, not all is bad. Lifetimes of those vacuum deposited cells can be extremely good for certain material systems. These ones are definitely more than 20 years lifetime under real conditions, so that systems have shown inherent stability under accelerated stresses, and even if you look at UV. Another point is that efficiency is not everything. You need to translate that also from lab to fab, and a vacuum deposition is being, vacuum deposited organic solar cells are being currently commercialized with linear evaporation sources rather than just the point sources we use in our labs, and wide roll-to-roll plastic substrates. And the picture on the right is really from the fabrication line in Heliatech. This is where they make their vacuum deposited organic solar cells, and the nominal capacity is 1 million square meters a year of this roll-to-roll coater, 1 meter 30 wide, I think, and 2.6 kilometers long. But going back a little bit more into the science is trying to understand where the energy losses come from in organic solar cells and what we can do about them, because that will decide material design, processing conditions, and many other things. And as I said, this work has been led by Anna Jungblut, and I'll quickly go through the main steps of free charge generation and the energy losses we observe. So photoabsorption leads to an exciton hole pair on the donor or acceptor, in this case on the donor on tab C. And then you have the charge transfer state coming into play where the electron is transferred over into the acceptor. And then hopefully we'll get free charge carriers at some point. But there's a whole discussion around how the disorder of the materials themselves, but the disorder in particular of the charge transfer state, leads to increased losses, and trying to understand where this is happening or why is that happening is important. The NFAs have been really good in reducing the offset between the S1 and the charge transfer state, and in the generation of free charge carriers. For fullerenes, there seems to be some bottleneck, and trying to understand what's happening there. While fullerene is not the most efficient material, it's still commercialization relevant, as long as the non-fullerene acceptors are as expensive as they are for many startups. Even those working in solution processing, the fullerene derivatives are the place to go. Now, this broadening at the CT state comes from, oops, is that as small on your slide as it is on my slide?
Looks pretty small to me.
Yep. Well, we were looking at nanoscopic systems, but that wasn't intended. So I hope the other figures in this presentation are the right size. So what I wanted to show here is static disorder is a measure of how donor and acceptor relate to each other, how they are they always in the same configuration, or are they in different configurations? Is, for example, the end closer to the 660 or the side closer to the 660? And you can imagine when you co-evaporate systems, or even when you solution coat systems, then there's definitely some static disorder. The dynamic disorder, similarly small, unfortunately. Sorry for that, but that is a temperature difference. Those are vibrations in the system, and they can have an impact. They lead also to the broadening of or disorder effects, and they are temperature dependent. And what we wanted to do and decide is how the donor choice impacts the energetic disorder, and how does the molecular aggregation impact energetic disorder, because we can play a little bit with this in our systems. Now, Anna looked in particular in those 4 systems that span a wide range of electronic quality and molecular properties, and also in terms of their energy level matching to C60. So we deliberately selected them. We've got TAP-C on the top left, which is a quite floppy material. It has been for some years now a workhorse for digging into the fundamentals of organic solar cells for ourselves and other groups. Rubrene, a relatively stiff molecule with a very, very low reorganization energy. Alpha-6T, a rod-like molecule, also relatively stiff, and copper phthalocyan, or the whole class of phthalocyanines, a disc-like molecule that we've been also using extensively. And as I said, we're using C60 because it's easily available, and B, there are no efficient non-fullerene acceptors that fly available yet. Now, the sample fabrication we did was a simple stack with ITO moly oxide and the active layer BFAN and aluminum made in our vacuum systems. One of the handles we can play with in our experiments is we can control the concentration of donor and acceptor relatively well throughout the film. And about 10 years ago, Ching Tang's group presented the concept of dilute cells, where you only have a 5%, to some extent you can call it contamination in C60, but actually it's not a contamination. It really works surprisingly well. So this is the donor C60 with 5 to 95%, those dilute cells. which we're using to disentangle microstructural effects from energetic effects, because in that dilute cell, C60 is the dominating host, and the microstructure is not gonna change as function of the donor, and the donor themselves have a relatively comparable environment, because depending on at 5%, they can be considered all dilute and only surrounded by C60. Whereas if you go to the 50-50 mix, you get changes in microstructure depending on the donor, whether it's an amorphous material or a crystalline material. And of course, you get donor aggregation that affects the local environment and the optoelectronic properties. So while we cannot yet image the interface directly between donor and acceptor, we've carried out GVAX measurement at ERSF of these films, mainly by Andreas Lauritzen, and then with the support from Olivia and Irfan in the group, to quantify what kind of ordering we get. And this is alpha 6T and neat alpha 6T, which we know is packing relatively well. And you can see quite some in-plane and out-of-plane features. And we use the number of these features to track how the films pack, and to be able to classify them, whether we have some ordering or non-ordering, and depending on how many of those features we can see. We carried out similar measurements for the mixed films, and also looked at the C60 ordering. You can imagine that you can still see some C60 ordering even in the 5% dilute cell, but once you went to higher concentrations, things become, well, the features are getting lost and weaker. Now, this is quickly how we classified it. If you looked at the donor aggregation features, if there's just 5% donor, we don't expect any aggregations, and the optoelectronic measurements later actually show that there is no aggregations. And then once we have to go to 50%, only copper PC starts showing some features in the GVAX, and then at 100%, TAPSI as amorphous material shows nothing. Rubrin actually shows a little bit, but alpha 60 and copper phthalocyanine are pretty strong shown. Now, let's go to the analysis of the charge transfer states at room temperature. So Anna built during her thesis a sensitive EQE setup that can measure the external quantum efficiency over more than 6 orders of magnitude, which we use to measure the EQE spectrum, and she's been working on corresponding fits and a program to fit everything to determine the charge transfer states. And the analysis was carried out in the framework of Markus Levitz-Jortner theory. And just briefly, Markus Levitz-Jortner, or MLJ theory, is an extension of the classical Markus theory, which is often being used to analyze charge transfer states. However, it neglects vibrations and the main, their internal and external vibrations. And Markus theory is applicable as long as they are smaller than room temperature, the energies, but for many organic systems, I don't think this is a valid assumption. And Markus Levitz-Jortner at least deals treating the internal vibrations quantum mechanically. This is where the Huon-Riss parameter comes in, and then the rest is relatively as before, charge transfer state, reorganization of charge transfer state, and so on. And you've got then, when you focus on the relevant parts for us, where we look at, we have 2 components that contribute to the total disorder, and that's the dynamic disorder, which makes up the first part as temperature dependent, and the static disorder, and it appears both in front and then in the exponent. And that is what Anna has then been analyzing in the various, or for the various material systems. Here we have TAPSI and rubrene. In both cases, the charge transfer state hardly moves when we go to 50% mixtures. And if you look at the other systems, well, that's an indication that there's little aggregation, TAPSI and the rubrene films, as also confirmed from our GVAX measurements. However, when we look at the alpha 60 and a copper phthalocyanine, we can see that the charge transfer state shifts considerably with the mixed films. Of course, there's always one thing to keep in mind, that the absorption of the dilute cells, given that the most absorption is in the C60, is relatively weak. That's why we get the vertical shift, so we get more, but we also get an energetic shift. And the CT state is decreasing with donor content. We attribute that to the molecular aggregation. We get that films, and this aggregation is also shown in, or confirmed with the or inferred from the GVAX measurements. As I said, we can't see individual donor acceptor ordering, but we can see a general trend of how the films are being, or how much aggregation they show. Now, this is at room temperature. To be able to figure out the static and dynamic disorder, we have to carry out temperature-dependent measurements. And this is here shown from above room temperature to 150 Kelvin. You can see a broadening in the charge, or in this feature in the charge transfer states. And when we fit this as over temperature, using the static and dynamic disorder from the previous formula, then we can work out which parts are static and which parts are dynamic in this case. And Anna carried out a long series of measurements for all these material systems. And what we found, that static disorder is typically larger than dynamic disorder at room temperature. For the TAPSI case, they are both approximately equal, but for the others, the static disorder is bigger. TAPSI is the most floppy molecule, the most amorphous molecule which we use. And then with rubrene and alpha 6T, both values increase with going to the mixed film, which is also not a surprise, given that we have more aggregation and a more complex microstructure than just C60 with something dispersed into it. And for copper phthalocyanine, things remain largely constant, and rubrene in terms of shows kind of the lowest, or some of the lowest values we have observed. Now, another way of plotting it in terms of comparing the static disorder is, if we look at by magnitude, we can see that alpha 6T both has in the dilute systems and the mixed systems the highest static disorder. Again, it's one of the most crystalline materials we've been using. Rubrene is relatively stiff, and we hypothesize that in the dilute systems it decides of how much the C60 matrix is actually interrupted by the addition, and in the mixed systems we get the aggregation between donor and donor that leads to this static disorder. And we have different domains growing there, and that kind of can be illustrated here with alpha 6T, where you have it surrounded by C60 in a matrix, and I'm glad that this molecular structure didn't shrink to nanoscale. Here we have it in a more 50-50 or in a bigger system, so we've got different orderings at the interface to C60. Now we've also carried out the comparison with respect to the dynamic disorder. There the picture is not as clear. We can see that alpha 6T actually has the same value as copper phthalocyanine and TAPSI in the same order. Just rubrene as a special molecule has the lowest dynamic disorder, and it's also known from CT state measurements that it has probably the steepest shoulder or the lowest reorganization energy in these fits, given its molecular structure. Okay, so with that, I'm already coming to the end of my presentation. As I said, organic solar cell commercialization is happening already via vacuum deposition with sizable machines and areas produced each year. The gaps for the vacuum field, so if there are any synthetic chemists in the audience, is evaporable non-fullerene acceptors. We think would close the efficiency gap towards the approaching 15 or 20%. And one thing that we are actively working on, and I think that's a complete different talk, is the microstructure and the end of the goal to linking what we see in our optoelectronic measurements, in our transport measurements, to the microstructure. And to summarize the electronic disorder part, we found that for most of our systems, the static disorder is larger than the dynamic disorder. What I haven't shown, but Anna has showed in her experiments, that the non-relative losses increase with energetic disorder. This is also what, for example, the groups of Barry Rand has shown, that the higher the disorder, energetic disorder is in the CT states, the higher the non-relative losses. And of course, we want to optimize them. And for example, since static disorder is higher, that might give us some design criteria for the new molecule engineering to have clean interfaces between, or less disordered interfaces between donor and acceptor. And what we've also found, that the static disorder increases with heterogeneous aggregation in our systems. And again, there the strength is that we can play with concentrations and go from dilute systems to mixed systems. And with that, I would like to again acknowledge our group and our funding. And yeah, thank you very much for your attention.
Thanks very much, Moritz. That's great. So please, audience members, feel free to start typing any questions and answers into the Q&A box.
Yeah.
In the meantime, I'll kick off. I just have a question or two.
Sure.
It's this point around the lack of non-fullerene acceptors. So the sorts of molecules Jason was showing are relatively large and relatively complex in order to build in the various donor acceptor type characters and quadrupole moments and rigidity and intermolecular interactions that were seen to be important. So does that place a bit of a practical limit on evaporable molecules? I mean, what sort of molecular weight would you stop being able to evaporate the molecule, and does that then place these sorts of limits on the molecular design?
So yes, there are some size limits, but there is no hard limit. The rule of thumb usually is 1,000 grams per mole, but we've got some molecules that break and are not evaporable, even much smaller than that. And we've got some molecules that fly at larger size. So it really depends how stable that molecule is. And a usually good test is look in TGA analysis, see when the molecule decomposes, and then compare that when you can start subliming it in a simple sublimation, well, evacuated glass tube or things like that, a thermal furnace that does the job. So yes, there are limits to the size of the molecule. However, there are also some advantages of having small molecules, and we see that in the OLED display industry, where, say, the lifetime came largely through ultra pure systems. You could sublime them. You can use the same process that you use for depositing the thin films. You can also use for purifying the molecule. So you start with very pure materials, and I think a similar advantage is also to the small molecule non-fluorine acceptors, that the synthesis can be cleaner than the polymer synthesis, even though you may not be able to purify them. And whether it is a fundamental size constraint that we can't find non-fluorine acceptors that are small enough to fly, I doubt it. It's more the questions of how many chemistry groups around the world are synthesizing non-fluorine acceptors for solution processing, and how many chemistry groups around the world are synthesizing smaller non-fluorine acceptors. For example, we're lucky to have Ian McCullough here in Oxford now, and yeah, we're looking into some of those potential smaller alternatives.
Okay, thanks. There's a question in the Q&A now from Maniket Rana. Dynamic and static disorders are deep or shallow traps?
That's a good question. So in terms of the values, the charge carrier or the CT still will always relax to the smallest one, to the lowest one. Let me just quickly go back to the corresponding slide. That's the one. So there, I don't know, can you see? Where's my mouse? Can you see
yes,
my mouse?
Yes.
So here we've got the disorder that leads to different energetic levels the charge transfer state can fall into, and it's usually gonna relax down to the lowest. I'm not sure whether I would quantify this disorder here as traps, because I think the overall the charge transfer state might be considered itself as trap with respect to free charge carriers, because that's where it starts combining through. But we also can see that even from the lowest part, we can still generate free charge carriers. So I'm not sure whether I would quantify that as generally as a trap there.
I suppose if the trap becomes shallow enough, it stops being a trap. So
yeah. Well, that's what we try to do with, say, can we engineer the interface, and can we reduce, say, the static disorder? The dynamic disorder we can engineer only with molecular, well, both can be engineered with molecular design, but one is more the internal one and one is more the external one between molecules. And there's been great work from Henning Siringshouse group in Cambridge about transport and reducing the vibrations in between molecules, or the molecular freedom, and just turning off complete modes that have led to much higher mobility as a result. So I think quite a lot can be done on the synthesis side to engineer cleaner interfaces, but also make molecules stiffer.
Okay, thanks. There's one more talk in the Q&A. Super interesting talk, Maurice. Do you expect the aggregation of the donors in blends affects electrostatics significantly, especially for alpha-6T? Effects of orientation and aggregation in neat films have been shown to affect this. Yeah,
short answer, I would think so. Question is how to best probe it. So I think we are still carrying out some more experiment in that area and trying to disentangle it. The optoelectronic measurements give us the device relevance. The microstructural measurements give us a handle on how the films are formed, but whether we see the right microstructure, meaning can we really determine how donor and acceptor are oriented with each other, and which are the ones where the main processes actually happen, is still a long way to go, I think.
Okay, we don't have any more questions. So let's thank Maurice again for an excellent talk, and I'll do the clapping.
Thank you.
So that brings us to the end of our three speakers today. For anyone who joined late, unfortunately, Rachel Evans wasn't able to join us, so we don't have a fourth speaker. But we did build in a bit of time for general discussion, in case there's any meta questions relating to the bigger field that anyone wishes to ask at the end, that we could share amongst the various speakers. It depends on how busy people are, whether or not we generate many of those types of questions in that sort of discussion. But maybe I'll just ask a bit of a meta question. It's been a nice balanced session where we've had presentation on perovskite solar cells, on solution processed OPV, on evaporated OPV. All of these are vying to some extent to fill niche markets at this stage. Of course, crystalline silicon is still going to dominate the mass-produced solar cell market for some time, but there's things it can't do well, so there's niche markets opening up. Just wonder if any of the speakers have any kind of comparative thoughts on whether these technologies, the different types of OPV and perovskites, are they competing against each other, or are they to try and fill the same niches, or are there distinctive niches that they could separately address? Is there space for everyone in these emerging fields? Just wonder if any of the speakers have thoughts on that they'd like to share.
Maybe I can speak first. Okay, thank you. I think compared to like inorganic based, silicon based photovoltaics, we know that there is a lot of advantages, not just only light, transparent, large area, low cost, blah, blah, but I think that the main advantage, the uniqueness of organic semiconductor-based PVs lie in the different applications, particularly if you are thinking about low light, indoor kind of application. I think there are a lot of studies already demonstrating much more efficient kind of device made with organic semiconductors. Of course, partly due to the tunability of organic semiconductor matching with your light source, not just only, of course, sunlight, but also indoor light, and much more efficiently being able to tune these optical properties of organic semiconductor, as well as perovskite, that they will give very unique kind of advantages of these new PV technologies. And of course, we can also think of, even though the silicon-based or other types of inorganic semiconductor already implemented in a lot of outdoor kind of application. If you are thinking about like agriculture-based greenhouse kind of PVs, or even like a building integrated kind of photovoltaic power generation, I think all these things we can maximize the functionality of like organic semiconductor in order to produce much better PV characteristics. So I can see as a niche market, there are a lot of things we can consider making use of indoor properties and semi-transparencies and so on.
Thanks, Jason. I'll just repeat the question for Maurice, whose computer crashed. I suppose my question was, the different technologies we heard about this morning, do you see them as being competitors with each other? Because they're all kind of emerging technologies in different ways. Are they competitors with each other, or are there distinct niches where evaporated or solution processed OPV or perovskites might separately succeed alongside each other? Is there space for everyone?
I think there's a space for everyone. We just had the IPCC report. There's not even a space for everyone, but there's, I think, a need for everyone. And we basically have to make use of all surfaces that we can. And yeah, so I think there's still a lot to do, and time is running. When you look at the CO2 carbon budget we've got remaining, we've got this decade to stem it. And I think we should rather see the synergies between each of our fields. And I think that's also what I liked about the webinar. It was about organic materials, but organic materials can be used in a whole range of applications to use and accelerate photovoltaics, whether it's a transport materials in perovskite or as itself as an absorber material. I'm still to see a research group who use perovskite as transport material for an organic solar cell, but hey, who knows?
There's Mercury Canisides used a perovskite material as a transport material in a dye cell some years ago. Maybe not in an organic cell. Emilio, anything to add, or are you still there? No, Emilio's overwhelmed with the information overload this morning. Okay, so thanks for those kind of closing off, rounding up remarks. There's no other questions being appeared in the questions and answers, but I think we've had some great discussions and some great responses and insights from the question and answer during the actual talks. I was pleased to see that we had really good attendance numbers today. Nobody really knew how these types of online webinars would hold up once the pandemic was over and people started moving around again. But there still seems to be a good niche for this type of short and snappy, easy to attend type online seminar. So it's great to see that a large number of participants found benefit in this event today as well. So we'll just round it off there. It just remains to thank all of our speakers today for an excellent session. Thanks to Supergen Super Solar for organisation and coordination and publicity, etc. Thanks to all the participants who took part, and especially those who submitted their questions and joined the discussion. That's been great. I've enjoyed it. It's been excellent to catch up with people online. Hope to see you all in person again sometime soon, and enjoy the rest of your day. Thank you very much.
Thank you very much. Have a great day.